In this video, we're going to introduce strong induction. So we've already talked about typical induction or normal induction, or sometimes it's called weak induction. And now we're going to introduce a strong induction, which allows us to do slightly more complex things. It's actually equivalent to the induction we've already done, but it's structured in such a way that it seems a little easier to work with. You can actually do a proof to prove that the strong induction and weak induction are really equivalent. So it's not actually more powerful, but the way we set it up makes it seem more powerful. Okay, so what we're going to do is we're going to try to prove that any integer greater than 1 is divisible by a prime number. So remember, prime numbers are numbers that are divisible only by 1 and themselves. And the first several prime numbers are 2, 3, 5, 7, 11, and so on, where 2 is the only prime number that is even. So we got that right there. So we want to do a proof by induction here. And this proof by induction, we're going to need a base case. So if you think about it, what's the base case? We start by saying that prove that any integer greater than 1. Well, what's the first integer greater than 1? It's going to be 2, right? So our base case is going to be 2. It's going to be the first number, the first prime number, and it's the first number in our sequence. It's the first integer greater than 1. So, as we mentioned, 2 happens to be a prime number. That's not required here, right? Because this is just looking at any integer greater than 1. It doesn't have to be a prime number. But 2 itself is divisible by 2, and as we said, 2 is a prime number, and so our base case meets its property. And in fact, recall these definitions. A number is prime if and only if it is only divisible by itself and 1. In this case, 2 is only divisible by 1 and 2. And an integer is divisible by an integer, a, if and only if it equals that a times another integer b, right? So we can say formally n is divisible by a if and only if n equals a times b for some integer b. So this is how we set up the definition of divisibility. Okay, so we've done the base case. Let's talk about the inductive step. In the inductive step, the very first thing we want to do, as always, is the inductive hypothesis. So think about this for a minute. Whenever we do an inductive hypothesis, we're going to look at the statement we're trying to prove, right? And we want to suppose that this statement works for some k in the range that this proof is supposed to cover. Right? That's how we do an inductive hypothesis. So we want to suppose that some k is divisible by a prime number where k is an integer and k is greater than 1, right? We need to specify. We know that we're only talking about integers here, and we're only talking about integers that are greater than 1. So both of those conditions we want to make sure we clarify in our inductive hypothesis. And now we want to think, what do we want to show? Well, in proofs by induction, we always want to show that this thing is true for k plus 1, right? So we want to show that k plus 1 is divisible by a prime number. Okay, so coming up with the inductive hypothesis and what we want to show should be becoming fairly straightforward to you at this point, right? We always take what is it that we're trying to prove, and we're going to suppose it's true for some k in the range that we're looking at. And then we always want to show that the property is true for k plus 1. This is where the proof starts to get a bit more difficult, is what do we do now? Well, I've got this k plus 1, so let's take a look at it. We've got k plus 1. And what do we know about k plus 1? Well, using the inductive hypothesis, we know this is equal to some number that's divisible by a prime number, that's k, plus 1. But divisibility really doesn't work so well with addition. Divisibility has to do with multiplication. And so this isn't going to work, right? This isn't going to take us anywhere, and we're going to get stuck if we try to go this route, because we're not going to be able to work with this. And in fact, this is where traditional proofs by induction kind of break down, is anytime you are trying to work with addition, when you have a problem that really needs something like multiplication or division. So here, divisibility has to do with multiplication and division. We want to be able to divide this whole problem up, k plus 1. We're not going to be able to just look at k and come to some conclusion. So this is where we need something stronger. This is where we bring in strong induction. So the method of strong mathematical induction is fairly similar to traditional induction. As we said, you can create a proof, a fairly simple proof that the two are equivalent. So just as with traditional or weak induction, we want to prove that for all integers greater than or equal some sort of starting point, base case, that some property of those integers is true. So what we do is step one, we still do the base steps or base cases. And here's where we start to differ in the fact that before with weak induction, we only ever have one base case. But with strong induction, we might have more than one. And I'll talk about why this is in a minute. But here could potentially, not always, we always have at least one, right? We always have at least one. So here we start, our starting point is at A. So we certainly have to prove that the property is true for A. But sometimes, and this will become, again, more apparent as we continue, sometimes we have to do more of it. So here we're doing it for A plus 1, A plus 2, all the way up to some B. So we're going to work this out. I'm going to write this up here. We're going to work it out for A plus 1, A plus 2, all the way up to B. Okay, and B is just some other integer that's bigger than A. Okay, and so once we've done these base steps, then we have the inductive step, and the inductive step is similar with one very important difference. Instead of assuming or supposing that the property is true for some k, we now want to suppose that it's true for some k and all the elements before it. So this is where it becomes a stronger statement. This is where we get the strong induction and how it differs from the weak induction. So notice here we say some integer k greater than or equal to b. So if we look back up here at our little number line up here, I don't know where k is, but k is going to be somewhere after b. And now what we're supposing is not just that the property works for k, which is what we used to do in weak induction. Now we're supposing that the property holds true for this entire list. Okay, and that's the really critical point. We're going to suppose that whatever property we're looking at, in this case, the example we're doing is that all numbers greater than 1 are divisible by prime numbers. So we're going to suppose that for some integer k greater than 1, all the numbers between 1 and k are divisible by a prime number. And by doing that, that's going to allow us to finish the proof. Okay, so this is going to be our inductive hypothesis. And just as before, we're going to want to show that p of k plus 1 is true. So that doesn't change. Now, this can be confusing for people because we're adding two new variables here. right? We're adding this b, which is the upper end of our base cases. And now we're adding this I. And this I is just the variable that specifies the range of our inductive hypothesis. All right, this is our inductive hypothesis. So we're kind of adding some variables, and it's really important to keep track of your variables. I think that's where most students have problems with strong induction, is just there's new variables. Now there's a lot of variables. We have n, we have a, we have b, we have I, we have k. It's a lot of things going on. So the biggest trick here is to keep track of what's going on. And this is sometimes written, because of this, we can kind of get rid of the I if we say something like a, or, you know, if we know that, let me undo that. If we know that our starting range is 1, for example, we might say something like 1, 2, ... k. Because that allows us to get rid of the I. Right? We kind of take the I out of the equation. An alternate way of writing this, of course, would be 1 less than or equal to I less than or equal to k. So these are two equivalent ways of writing the same sequence. But sometimes having that I in there can confuse people. So you can kind of choose whichever way you like. Right, and this is, we call this strong induction because we're making a stronger statement here. We're making a much stronger assumption. We're assuming that this property is not just true for a single value, but now that it's true for an entire range of values. It's true for this entire range up here at the top. And our domino analogy that we talked about in a previous video, this still works, except now instead of assuming that one domino gets knocked over and we want to see if it knocks over the next one, we're just now assuming that all the dominoes at the beginning fall over and we want to see that the next one falls over. Okay, so let's come back to this proof. We want to prove that any integer greater than 1 is divisible by a prime number. In this case, we don't need more than one base case. So our base case stays completely the same, right? Because we don't have, we'll see some more examples where we'll use more than one. Okay, it's when we get to our inductive step that this starts to change. So now for my inductive hypothesis, I want to assume that a range of numbers, all the numbers up until k, are divisible by a prime number. Not just k. If you recall back, we had said just k was divisible by a prime number. Now I'm saying all the numbers are divisible, up to k are divisible by a prime number. And we can write that using this notation as well. And just as before, we want to show that k plus 1 is divisible by a prime number. So this is really the only part that's changed. So we're strengthening our assumption. We're making a stronger assumption. We still can't assume that all numbers are divisible by a prime number because that's what we're trying to prove. But we can assume this. Now, the way we're going to do this is I'm going to break this into cases because we're looking at a number k plus 1. We want to look at this number and say, we want to show that it's divisible by a prime number. Well, case 1, that number k plus 1 could be prime by itself. Right? Maybe that k plus 1 is 11 or 5. Well, then it's a prime number all by itself. And if it's a prime number all by itself, then it's divisible by itself, which is a prime number, and we're good. So 5 is divisible by 5, and 5 is a prime number, and so it's divisible by a prime number. So this is the easy case. If k plus 1 is prime, then we're golden. The harder case comes in when k plus 1 is not prime. And up here, I've rewritten the theorem we're trying to prove, the induction hypothesis, and what we want to show. So we have these for reference. So case 2 is that k plus 1 is not prime. Now, if we think about the options, if you recall, there are 3 options. A number can be prime, composite, or less than or equal to 1. However, since we're told that this number has to be greater than 1, and we know that it's not prime, we can conclude that the number is indeed composite. So we can use the definition of composite, which we talked about in module 4. Module 3? I think module 3 actually. So this is the definition of composite. So if we say k plus 1 is composite, then we're saying it must equal a times b, where a and b are integers, so the a times b, where a is between 1 and k plus 1, and b is between 1 and k plus 1, right? Because the definition of prime is it's only divisible by 1 in itself. So if it's not prime, if it's composite, we're saying, well, it's got to equal two numbers multiplied by themselves that aren't just 1 in itself. But also, if you look at this equation, this can be rewritten. If I put greater than or equal sign here, this 1 can become a 2, right? Because if it's greater than 1, and we know it's an integer, another way of writing that is it's greater than or equal to 2. And if it's less than k plus 1, we can say it's less than k, right? Because these equal signs kind of allow us to shrink the range. I mean, the range is the same. We're not changing the numbers at all. And so if we rewrite it for both sides, we get that a is between 2 and k, and b is between 2 and k. All right, so this is the definition of composites, this first line. But by shrinking these in and making them, instead of greater than, making it a greater than or equal, instead of a less than, making it a less than an equal, I've now got it in this format. I want you to notice something. A is between 2 and k, which is exactly what we have in our inductive hypothesis. So that means that A, by our inductive hypothesis, is divisible by a prime number, right? Because it's in that range between 2 and k. Okay, so this is the real crux of the proof, is that noticing that because we know that A is between 2 and k, it falls into this range that we supposed in our inductive hypothesis was divisible by a prime number. So we know it's divisible by a prime number. In fact, B is 2, but we don't actually need that. So because of the definition of divisibility, I can say that A is equal to P times Q, where P is a prime number and Q is just some integer, right? Because it's divisible by a prime number. This is the definition of divisibility. And as I said a moment ago, the real key is that I don't know where in that range A falls. I don't know where it is. I don't know if it's 2. I don't know if it's 10 or k minus 3. I don't know what it is. But because we're using strong induction, if it's in that range, I know it's prime, right? Because that's what we said here in our inductive hypothesis. If it's in that range, it's prime. So we said that k plus 1, so again, coming back here, we sort of started right here saying that k plus 1 equals A times B, and we figured out that A equals P times Q. So putting those pieces together, those are those two pieces, we get that k plus 1 equals P, Q, B. So P times Q times B, where P is prime, and Q and B are just integers. And now we can start just doing some of our standard proof techniques. I can let Q times B equal some integer Z, and I can notice that Z is an integer under integer closure properties. So now I can say that k plus 1 equals some prime number times an integer. And yes, this step is necessary because our definition of divisibility is some number times some integer. Some number, we're divisible by a prime number, which is P times some integer. It's not times 2 integers multiplied together, right? This is not fitting the definition of divisibility. We have to go through this intermediate step. So, but now we can use the definition of divisibility because we've put it in the correct form. And now we can conclude that k plus 1 is divisible by p, which is prime. And that is what we wanted to show. Okay, so again, the trick to this is by supposing that all the numbers in this range are divisible, I don't just have to look back one. In weak induction, we can only go back one step. In strong induction, I can go back however many steps are needed using divisibility, right? So I'm no longer just using addition, I'm using division. And that's what it allows me to do.